A 744 billion parameter AI model should not run on a laptop with 25 gigabytes of RAM, and technically it doesn't. That is the trick. This is GLM 5.2, one of Z.ai's largest open-weight models. Z.ai describes it as a 744 billion parameter mixture of experts model with roughly 40 billion parameters active at a time. It also supports a 1 million token context window and is released under the MIT license. If you downloaded the model at BF16 precision and tried to load it normally, you would be dealing with roughly 1.5 terabytes of weight. The official Hugging Face repository itself is around 1.5 to 1 terabytes. So putting this model into 25 gigabytes of memory sounds impossible. Because it is. The whole model never goes into RAM. Instead, a small open source project called Colibrì does something much more interesting. It treats your SSD, your system memory, and, if you have one, your GPU memory as different levels of the same giant memory system. The important parts stay close to the CPU. The rest of the model lives on your SSD, and when GLM 5.2 needs a specific piece of itself, Colibrì pulls that piece from storage, uses it, and moves on. It is almost like virtual memory for an enormous neural network. And the reason this works starts with the architecture of GLM 5.2 itself. Most language models are easy to misunderstand when you hear their parameter count. If somebody says a model has 744 billion parameters, you might imagine all 744 billion participating in every single word it generates. GLM 5.2 does not work like that. It is a mixture of experts model. After the first few dense layers, its feed-forward network is divided into hundreds of smaller experts. Each MOE layer contains 256 routed experts, plus a shared expert. But for each token, the router selects only 8 of those 256 routed experts. The rest do nothing for that token. Across the network, Z.ai says that only around 40 billion parameters are active during a forward pass. That is only a small fraction of the model's 744 billion parameter total. And that changes the problem completely. You still need to store the entire model somewhere, but you do not necessarily need every parameter sitting in your fastest memory at the same time. Colibrì takes advantage of exactly that distinction. First, it separates the model into two broad groups. There is a dense core, things like attention, embeddings, shared experts, and other weights that are repeatedly needed. Colibrì estimates that section at roughly 17 billion parameters. In its current INT4 format, that resident portion takes around 9.9 gigabytes. That stays in RAM. Then there are the routed experts. GLM 5.2 has 75 MOE layers with 256 routed experts in each, plus another set associated with its multi-token prediction head. Colibrì exposes 19,156 routed experts in total. Those experts make up the enormous part of the model, and instead of keeping all of them in RAM, Colibrì leaves them on the SSD. The current recommended Colibrì container for GLM 5.2 is around 372 gigabytes. So this is an important distinction. A 744 billion parameter model has not somehow been compressed into 25 gigabytes. You still need hundreds of gigabytes of fast storage. What has disappeared is the requirement to keep hundreds of gigabytes of weights in RAM at the same time. That is a very different breakthrough. Now imagine GLM 5.2 generating one token. The router reaches a mixture of experts layer and decides which 8 experts it wants. If those experts are already cached in fast memory, great. If not, Colibrì reads their weights from the SSD. The CPU runs the computation. Then the engine moves to the next layer, and the same process happens again. Across an entire token, only a subset of this enormous expert library actually has to move. According to Colibrì's measurements, roughly 11 gigabytes of routed expert weights change from one token to the next. So instead of asking, how do I put a 744 billion parameter model into RAM? The system asks, how quickly can I deliver the small part of this model that the next token actually needs? And suddenly, the most important component in the computer is not the GPU. It is the storage system. Colibrì uses several tricks to reduce how often it has to wait for the SSD. It keeps a per-layer cache of recently used experts. It can learn which experts are repeatedly hot for a particular workload and pin those in faster memory. It can prefetch experts for the next layer while the current layer is still computing. The project reports that routing is predictable enough one layer ahead to make this useful in many workloads. It can even spread reads across 2 SSDs. This is less like traditional model loading and more like a tiny operating system specifically designed to move neural network weights between storage tiers. But now we get to the catch, and it is a huge one. This thing is slow, On the original, roughly 25 gigabyte development machine, Colibrì reports about 0.05 to zero point 0.1 generated tokens per second in the cold, heavily streamed configuration. At zero point 0.1 tokens per second, a single token takes around 10 seconds. Not an entire answer. One token. So no, this is not replacing ChatGPT on your laptop. You are not going to have a natural back and forth conversation at that speed. A response that would normally stream in seconds can take many minutes. A long answer could take dramatically longer. But the slow speed is actually what makes this project interesting. Because Colibrì is showing that memory capacity and inference speed are two different problems. Traditionally, if a model does not fit into memory, you simply cannot run it. Here, insufficient fast memory does not necessarily stop inference. It moves more weights down the hierarchy, from GPU memory to system RAM, from system RAM to SSD. You pay for that movement with speed, but the model can still execute, and as you give it more memory, the exact same approach gets progressively faster. Colibrì reports around 1.8 tokens per second on a 128 gigabyte CPU-only machine once the cache is warm. A laptop class system using an RTX 5070 Ti has reached about 1 token per second. And on a 6 RTX 5090 machine where the experts can remain resident instead of constantly coming from disk, the project has measured roughly 5.8 to 6.8 tokens per second. Same basic model, same basic engine. What changes is where the weights live. And there is another reason this is more than a stunt. GLM 5.2 is actually a serious model. Z.ai reports a score of 62.1 on SWE Bench Pro, compared with 58.6 for GPT 5.5 in its published evaluation, and 81.0 on Terminal Bench 2.1. But that comparison needs an asterisk. You should not turn those numbers into the statement GLM 5.2 is better than GPT 5.5. Independent artificial analysis results, for example, put GLM 5.2 max below GPT 5.5 at its highest reasoning setting on their overall intelligence index. Different benchmarks, harnesses, and reasoning budgets can change the ranking significantly. The safer conclusion is that GLM 5.2 operates in a genuinely high-end class of coding and reasoning models while keeping its weights openly available. That is what makes the laptop experiment important. If this were a tiny distilled model, SSD streaming would just be a clever optimization. But here, the model is hundreds of billions of parameters larger than what a normal consumer machine could conventionally hold. And yet, the inference engine can still execute it locally. Painfully slowly, yes, but locally. No remote GPU is required for the basic CPU configuration, and once the weights are downloaded, the actual model inference can happen on your own machine. Colibrì's core engine is written in C and does not require a GPU to run. The setup is also surprisingly approachable for something this strange. Colibrì currently lists around 16 gigabytes of RAM as the minimum for GLM 5.2, with 24 gigabytes or more being comfortable. The real requirement is storage. You need roughly 380 gigabytes of free space, preferably on a fast NVMe SSD. There are pre-built Colibrì releases, and a pre-converted GLM 5.2 in T4 container is available, so you do not have to begin with the full BF16 checkpoint. Once the model is there, Colibrì can inspect your available RAM, storage, and GPU resources and decide where different parts of the model should live. And I think that is the bigger story here. For years, running large AI models locally has mostly been a compression story. Take a 70 billion parameter model, quantize it, make it fit inside 48 gigabytes, then 32, then 24. Colibrì is exploring a different direction. What if fitting the entire model into fast memory stops being a requirement? Mixture of experts models already give us sparse computation. NVMe drives keep getting faster. System RAM is cheaper than GPU memory. And software can become much smarter about deciding which weights deserve to live in which tier. That does not make hardware irrelevant. Physics still wins. If your SSD has to deliver gigabytes of weights for every generated token, storage bandwidth becomes a brutal bottleneck. Caching helps. Prefetching helps. More RAM helps. GPUs help enormously. But none of those change the underlying idea. A model can be much larger than the machine's RAM and still be runnable if the model is sparse enough and the runtime is smart enough about moving its weights. So the headline is not really 744 billion parameters fit into 25 gigabytes. They don't. The more accurate headline is much more interesting. For the first time, we are seeing a 744 billion parameter open weight model treated less like one enormous object that must be loaded into memory, and more like a library. Most of the library stays on the shelf. The router asks for 8 books. The system pulls them down, uses them, then moves on. Today, that library is painfully slow to search. Tomorrow's SSDs, larger memory systems, smarter caching, and better inference engines will make it faster. And that may be the real lesson from Colibrì. The question for local AI may no longer be, can the model fit in my computer? It may become, how much speed am I willing to trade to run a model that doesn't? And that is a much more interesting future. If you enjoyed this breakdown, subscribe to Code Unpacked. There are a lot more supposedly impossible AI systems that become surprisingly simple once you unpack how they actually work.